Hello and welcome to my channel. You are watching the Mad Computer Scientist. The Mad Computer Scientist is a proud member of Mad Scientist Local 42, where we ask if we don't play God, who will? Today we're going to talk about the biggest unsolved problem in theoretical computer science, and that is P versus NP. If you are unfamiliar with this problem, you're probably asking what it's about, and that is a good question. Well, you do know that some people find some problems harder to solve than others. For example, a calculus problem versus simple addition or solving a Rubik's Cube versus petting your cat when she's crawling on your shoulder. Much like humans have a hard time solving some problems and find some problems trivial, computers also have a more difficult time solving certain problems than others. And this, in essence, is what P versus NP is all about. So you're probably asking yourself what P and NP are, and that is a good question. These are sets. P is the set of problems that can be solved in polynomial time, i.e. we can express its runtime complexity as a polynomial, and NP are the set of problems that can be solved in non-deterministic polynomial time. Believe it or not, all problems in set P are also in NP. What is not known right now is if P is a proper subset of NP if you're a math nerd, or if it's just a subset of P and the sets are identical. The major difference is that although any problem that can be computed can be solved in NP time or faster, it's just that NP problems take more computational time. Some examples of famous NP problems are the traveling salesman problem, the three satisfiability problem, the coloring graph problem, and if you want to know something about the Rubik's Cube I mentioned earlier, solving a Rubik's Cube is a 3D Hamiltonian graph problem for a computer. And yes, that problem is NP hard, as I mentioned. If we find out that the set of NP problems has all problems in it capable of being reduced to polynomial time, it means we can write more efficient algorithms to do some of the most complex and challenging computational tasks. At this point, you may be wondering how long this problem has been around. It appears that it's been known since the 1950s, although it wasn't formalized until Steve Cook wrote his 1971 paper, The Complexity of Theorem Proving Procedures. If you are wondering, Steve Cook is not in any way related to anyone at Apple. It is an entirely different person. He will, however, if you shut up, happily take your money. And here, at the Mad Computer Scientist, we always believe in being technically correct, which any Futurama fan knows is the best kind of correct. An earlier example of the problem being described occurs in a letter Kurt Gödel wrote to John von Neumann, the person who created the von Neumann architecture, describing the problem. John von Neumann was suffering from cancer at the time, and it is not known if he ever read the letter Gödel sent him. You're probably wondering what the implications of this are, or why computer scientists are bothering with it at all. After all, any computer scientist worth their salt will do something simply because they can, not because they should. And in fact, that's why computer science is currently a mess when it comes to ignoring things like sociology. But if P equals NP, it has implications for cryptography, where it becomes nearly impossible. If P equals NP, it also turns out that programmers currently writing difficult algorithms to work on current tasks can simplify them to more efficient and less time-consuming algorithms. If you're wondering why this is important and need a more concrete real-world example, just think of companies like Amazon and Google. For these companies, in a very real sense, computational time is money, and the more time they're spending computational time on selling users things, and the less on looking things up to sell to users, the better for those companies. It also means in our daily lives we can get quicker responses from Google Maps and similar programs when we're asking them to find the shortest path to someplace we want to go. And for all of these things to be true, P must be equal to the set of NP. Now let us discuss the 5 possible worlds of P versus NP. Don't worry, a possible world just means these are the scenarios that can happen if we do finally solve this problem. The first is Algorithmica, where P equals NP, which is bad news for cryptography because it breaks a lot of our current algorithms and makes them impossible to be secured. The second is called heuristica. In heuristica, this is kind of a middle ground between the first and the third scenario we're going to talk about, where problems are only NP hard in the worst case scenario. This does mean we can still have cryptography algorithms, but they'll be harder to make. Pessyland is the pessimist solution. Basically, it is easy to create NP hard problems that we don't know an easy solution to. The fourth possible world is minicrypt. Minicrypt is a world where one-way hash functions are possible, but you have no public key cryptography. And the fifth world is the one security experts would love to have, is the world called cryptomania, where two-way hashes can exist. So let us talk about why no one has ever solved P versus NP. Part of the reason comes down to computer science being the offspring of mathematics. So far, no one has produced a proof that can show that all NP problems can be reduced to a P problem, meaning that the sets are equal. Or you can find one example that shows the sets are not equal and that's all you need. So someone has to show a proof that one NP problem can't be reduced to a P problem, and thus confirming that the sets are indeed not equal and that P is a subset of P. Are you a young, aspiring computer scientist who wants to earn $1 million? Well, why don't you go to the Clay Foundation Millennium Problems page and look at the problems that are there. Some of these are in computer science, some are in math. They offer $1 million for all of them, and solving the P versus NP problem would give you a good financial start, or at least pay off your student loans, as well as giving you fame that will help you throughout your career. Please note that in an earlier video, I might have said that the 3n plus 1 problem was on the list of Clay Foundation Millennium Problems. It is not. I apologize for any confusion that caused. With that being said, please remember to like, comment, and subscribe. Share this video out, and although this channel is fairly new, please check out some of my other content that the algorithm recommends. If you have ideas for future content, please post below. Also, stay tuned because we're going to add some math fun to this one. Now that we've discussed P versus NP, I thought we'd have some fun with some math problems I found online. Here's one I found on Twitter. We have 900 minus 625 all over 30 plus 25. Now, of course, we could just plug this into a calculator and get the answer of 5, but I wondered, is there any way we can break this down to make it a little easier for us? The first thing I did is realize these are all multiples of 5, so I factored out a 5 out of both the numerator and the denominator. And I know some of you don't believe PEMDAS works the way I'm telling you it does, but just trust me, if we're using PEMDAS rules, what I have typed under number 1 is correct. But ideally, I would want to type it out as a fraction again just to make it clearer. Unfortunately, I didn't have the space. So to simplify things further, we're going to remove the brackets from it and rewrite the problem as 5 divided by 5 times 180 minus 125 in parentheses divided by 6 plus 5 in parentheses. Again, I'm just doing this to make the problem less ambiguous, and as we all know, 5 times 5 equals 1. So since it equals 1, we can just remove that from our next step, leaving us with 180 minus 125 divided by 6 plus 5 with both terms in parentheses. Once we do the math, since they're both in parentheses, we're left with 55 divided by 11, which gives us 5. Now, of course, you could have just worked it all out by hand, and you probably would have and should have gotten the same answer. Have a great day, everyone.